On more complicated ones, you could then, after you did your mental work on transforming this and believing what you've got is correct, is kick it into your calculator and see it that way. Okay? Any questions? You can see how this course builds on stuff that came earlier. We've got this vocabulary of end behavior. See the end behavior? Y approaching 1 as x approaches infinity, off to the right, and similarly off to the left. We've got these asymptotes, a little bit of new vocabulary in there. We've got these transformations existing in here as well. We've got zeros. This function only has 1 0, it looks like, doesn't it? 1 0, and it does have a y-intercept. Question? Mm-hmm.
X or y first, like x approaches infinity is y equals 0 or something like that? Doesn't matter if you switch them around? And say the
No.
y first.
No, it doesn't matter. It's usually better to talk about the domain readings first, though. Watch this. And actually, your question was good. She was asking, if it didn't come across on the video, she was asking about, do you mention the x first or the y first when you're talking about the end behavior or approaching asymptotes? It's usually better to talk about the x first. So watch the mathematics. This is a fancy way to explain, and we've actually already done this. But what I would do here is I would say x approaches infinity. That means I'm heading off to the right. I go back up and look at the original function. And look at what r of x is doing. See if I can tuck it in down here. R of x, that original function, is approaching 2 divided by a huge number, isn't it? 2 over infinity up there. Because if you take 1, I don't know if you can see it, yeah. If you take 1 away from a huge number, that doesn't make much, that 1 doesn't make any difference, does it? No. Okay. And then we're adding 1 to that, right? Now look at what this combination is. Think about a number that is 2 divided by a huge number. That's really close to 0, isn't it? Isn't 2 over a huge number really close to 0? So the shorthand I like to use is, like I showed you earlier, is 0 with a little plus superscript. That's a slightly positive number close to 0. And we're adding 1 to that. Now look what happens in the limit as x does go towards infinity. In the limit, as x goes towards infinity, this approaches 0 and means you're adding a little bit to 1. Adding a little bit to 1 for these r values, which happen to be your y readings. So up here on the graph, if you can move the image up just a little bit, there we go. As you move further out to the right here, folks, here you're up 1, and the further out you go, you're adding less and less and less. That's what this mathematics indicates. And here it is graphically right there. Like the plane coming in for the landing. I'd like you to practice this a little bit when you see problems in the book, homework problems. Okay? Okay. Okay. Now, as we go off to the left here, let's do it similar to what I mentioned earlier. As we let x approach negative infinity, going to the left, then let's see what happens to r of x. We have 2 over a large negative number, looking up here, 2 over a large negative number, plus 1. And notice that this 2 over a huge negative number is what kind of number? Like 2 over 1,000, negative 1,000. 2 over negative 1,000,000. Very tiny again, near 0, but slightly negative, right? So the way I like to write that is 0 with a little negative superscript, plus 1, and that's what your y is approaching. So check this out. As you come off to the left, going to the left, you're up at 1, and you're taking a little bit away from, see this? You're taking a little bit away from this 1. And the further out you go, you're taking less and less away. I like to think of something physical. You ever seen a fly come up and land on a ceiling upside down? Right? Coming in for a landing up on a ceiling? Okay, so you can think of it that way as you're going off to the left here. Finally, last comment about this, actually almost the last comment on this function, is what's the domain of this function? All real, you see, if you look at the picture, you can see it. Negative infinity coming over to 1, trouble at 1. Negative infinity coming over to 1, trouble at 1. Better skip that spot. Pick up microscopically on the other side of 1, and off to the right you go. Look at the range. How low? Start low, like water level rising. Good, good, good. Everything's good until you get to good. Y values from negative infinity coming up to, help me, 1. Thank you. A gap there at 1 again. So negative infinity coming up to 1, trouble at 1, pick up just above 1, and continue on up. Okay, domain and range. Okay. Notice back now at the original for just a minute. This thing is a fraction plus a whole number. A fraction plus a whole number. In other words, we've got a fraction plus something else. Could we do something from beginning algebra with that? Couldn't we form this into a single fraction? It's just like you being back in elementary school, adding say, a fraction like 2/3 to 5, right? You need to get a common denominator and then build it into a single fraction. No different than what you did in arithmetic. So let's come over to this board. And do that. So we have our r of x is 2 over x minus 1 plus 1. Now I want to turn this into a single fraction. So I know that this is 1 over 1. My common denominator necessary here needs an x minus 1. So over here, I'm going to multiply this 1 times x minus 1, top and bottom, so that I don't really change this thing. It's still the original function because all I've done is multiplied this last term 1 times 1. We all know that. And so now we have a common denominator. There's our common denominator, and our numerator is a 2 plus x minus 1, which we can simplify to x plus 1 over x minus 1. Okay. This is the way oftentimes you will see a rational function presented as a single ratio of two polynomials. In this case, we have a linear polynomial divided by a linear polynomial. Notice the end behavior. By looking at this original form, the end behavior. How do we examine end behavior? What dominates the numerator? X or the 1? If x is big. If x is big, does 1 make much difference to it by adding 1? No. So that's what we mean by end behavior. X is big. Okay. What dominates the denominator? Again, x. Taking one away from a big number doesn't make much difference. Okay? So the dominant terms here, the dominant terms for end behavior as x approaches infinity is y is approaching x over x. The leading term in a polynomial is what dominates the polynomial. We talked about that a few class sessions ago. The leading term of a polynomial dominates it. Okay? So it behaves like x over x if x is large. And then look what happens to that. X over x reduces to 1. So as you move further out, here's how you can see that horizontal asymptote. If the degree of the numerator is the same as the denominator, then all you have to examine are those leading terms, like I just showed you here. Examine the leading terms in the behavior. Feel good? Okay. If you went towards negative, and now the one thing this approach does not tell you very well is it doesn't tell you if you're coming up from below or above, like I explained earlier. Like the airplane coming in for the landing out to the right, or the fly coming up to the ceiling from heading off to the left. Okay. The detail, the way I explained that earlier, gives you that detail. Okay. So that helps you get your end behavior for a horizontal asymptote. We have a fraction here, and in the introduction to this last session, I spoke of the numerator as being a function called n of x, and the denominator being a function called d of x. Textbooks oftentimes will take the numerator and call it p of x, and the denominator q of x. Doesn't matter what symbols you use. What would make this fraction 0? What will make r of x equal to 0 if you've got a fraction here, x plus 1 over x minus 1? Doesn't turning that numerator into 0 make this equation turn to 0? Okay. Or you can just look at this problem now. Look at this problem. 0 equals this fraction. Multiply both sides by x minus 1, and you lose the x minus 1. Right? If you multiply both sides by x minus 1, it disappears. And you end up with x plus 1 equals 0, x equals negative 1. Negative 1 if y is 0. There's your 0 of r of x. The 0 of r of x. So the way you find zeros usually on on rational functions is you let the numerator function take on a 0 value. And that's how you examine where your zeros are going to occur. Okay? How are you going to find vertical asymptotes on rational functions? If you're given this function as x plus 1 over x minus 1, vertical asymptotes are places where trouble occurs, aren't they? Where trouble occurs in x. And I heard somebody mention it. If the denominator goes to 0, you've got trouble. Okay, so if your denominator goes to 0, x minus 1 equals 0, x equals 1 is a place for trouble. You go back and try putting a 1 in here, folks, into your function, and you get a nice 2 numerator over 0, which is undefined. So this is how you find vertical asymptotes, usually. is by setting the denominator equal to 0. So this is going to be vertical asymptote. There's a lot of new vocabulary with these things, and historically these rational functions tend to cause people a little more trouble. The first step in understanding them is know polynomials first. Know polynomials fairly well. Secondly is, once you know the polynomials well, become familiar by talking to each other with some of this vocabulary, like the word asymptote, both vertical and horizontal, so forth. Okay? Typically, textbooks will give you a series of steps to analyze polynomials and a series of steps to analyze rational functions. I cannot remember those steps in order. I don't remember them at all. But all I do is I play with the thing. I play with it. I look for the easy things first, and then I start investigating it. And I try not to grab my calculator right away. Okay? So that's the way I would encourage you to play with these things. And also getting together with another person and talking it out is helpful. Okay, let's build another one. Because these things could get a lot more exciting than linear over linear, couldn't they? Okay, right? So, stay awake. Actually, you're probably so excited now you can't wait for the next problem. Okay. Any questions? Okay. We're going to work on this again tomorrow in the lab session. And then Friday, we're going to come back and do some more. So make sure you give this stuff some attention before Friday's session. Okay? And don't miss class tomorrow. Okay. Let's build one, a new one. Why don't we start with a factored form, just because that's more comfortable for most of us, if it's already given to us in factored form. Let's put a quadratic on top and a cubic down below. So we're going to have a numerator function and a denominator function, and we're going to put a quadratic on top in factored form. So what kind of zero might be a nice zero to have? X equals, huh? Negative 3. So that means if x equals negative 3 for a 0, then that means x plus 3 would equal 0, right? So let's put that up there. Feel good? Let's put one over on the right side, say out at 4. At x equals 4. So that means x minus 4 could equal 0. So we have ourselves a nice simple quadratic. Down below, let's build a cubic. Let's say we have a cubic that has a factor that's going to have a vertical asymptote at, say, x equals, how about 2? A vertical asymptote at x equals 2. Then that means, what do we have to put in our denominator? We need to make what in the denominator will make this whole mess turn to undefined, because that's where vertical asymptotes occur. X minus 2, right? Let's give that factor, or the 0 on that polynomial of 2, let's give it a multiplicity of 2. Okay? Let's lay another vertical asymptote on this thing. This is fun. So we're building the function. We're building the function up instead of just starting with some function given to us. So let's put one way off to the left, maybe over at minus, how about minus 6? If x equals minus 6 is another vertical asymptote, and I've got 4 minutes left. Okay. And so that's going to be an x plus 6 factor. Okay, so we're going to have zeros at -3, 0. Let's see if I can tuck that in, that information in over here. Zeros at -3, 0, and at 4, 0. And then we've got our vertical asymptotes already laid out here. So we got some good information from which we could start drawing some of this. Okay, so here we go. At 2, oh darn. At 2, we're going to have a vertical asymptote. At -6, we're going to have a vertical asymptote. I'm trying to model for you good behavior on your paper. Okay? You write the equations down, please. Okay. Now, we've got those two. Oh, we also have some zeros. At -3, we have a 0. And at 4, we have a 0. Okay, we've got 2 minutes left. And you're going, he's not going to make it. Okay, just watch. Okay. Everybody okay so far? I've got the information down that we've got. Now, what are our leading terms going to be, folks? If I start playing with r of x here, expanding this out, isn't this first term going to be x squared? The leading term with some other stuff on here, minus x minus 12. And then down below, I'm going to end up with an x cubed leading term with some stuff. I'm not even going to worry about it. And look at this, folks. Isn't there going to be on the tail end of that cubic a plus 4 times 6? See it? Plus 4 times 6, 24. And so look what happens for x equals 0. R of 0 disappears the x terms, and I'm left with minus 1/2, right? So that's a point, 0 minus 1/2. Can I go another couple minutes? Okay. So 0 minus 1/2 is a y-intercept, folks, right here. Okay, now I'm going to go fast on this. Next class session, I'll come back and go a little slower. I want to draw a picture of the numerator. The numerator is a parabola, right? With zeros here and over here, right? Okay, so I'm going to just draw it kind of like this. It's going to bottom out somewhere. Whoops. It's going to bottom out somewhere in here probably. Right? So everybody agree? That's your numerator, your quadratic function here, n of x. Okay. Now, the denominator is an x cubed function. Up 24. X cubed up 24. And then look at this. This one, this polynomial in the denominator, this cubic, has a 0 at 2 and at -6, right? And it's x cubed behavior. Means it goes up right and down left as a cubic. And where does it bounce off the axis? At 2, because of the exponent being even. And over at -6, it cuts through the axis over here. Okay, so I'm going to try to draw it. How about just dotted? Comes up through, let's see, what's it doing here? It's got to do this, doesn't it? Oh, a 2, not 4. Yeah, thank you. Thank God for erasers. Okay. So here at 2. So I'm drawing just the denominator function, right? Okay. Now, finally, in 30 seconds, we're going to draw this thing real quick, and then you could listen to this tape over and over again if necessary to understand it. What I'm doing here, I call these wiggle diagrams. I draw the numerator because it's polynomial, it's easy, parabola. I draw the denominator, it's a cubic, it's not too tough once you understand that, okay? And so then I look at the values I see here. Notice that the numerator function's positive out to the left here, and the denominator is negative. Positive divided by negative is negative. And notice the end behavior, x squared over x cubed approaches 1 over x, doesn't it? Which means it dies towards 0 off over here. So I know the graph is going to come in like this over here. As I go off to the left. Now in here, there's a vertical asymptote here. Can it do this? Can it cross that vertical asymptote? No, has to take a dive. It can't ever touch that vertical asymptote, so it has to do this over here. Now, look in this region in here, folks. Positives divided by positives. And near a vertical asymptote, it has to either blow up or blow down. So it has to blow up on this side because of the nature of positive divided by positive. And then we've got a 0 here. 0 here. And then in this region now, we've got positive readings divided by negatives, or vice versa. Negatives divided by positives are negative. And here's your y-intercept, folks. And so it has to do this. And then what? Here's a vertical asymptote. Negative divided by positive has to stay negative, doesn't it? Has to dive down there. I'll start the next class session out with this graph and more carefully done. And then finally, over here, positive divided by negative has to stay negative, has to come up through here. And then out to the right, notice positive divided by positive has to stay positive, so it has to sweep in like that and approach this horizontal asymptote out there. So the graph is, sorry about all this, it's this thing. This, that, and then coming up here like this, and dropping out like that. How do I check to see if we have it right? We put this fancy thing in our calculator with an appropriate viewing window based on these numbers we see here, not too far to the left, not too far to the right, and you should see that picture. I'll start the next class session out with this function with a little more explanation. Okay, that's it for today. See you tomorrow at 10.